Hello everyone and welcome back to the series. In this video, I'll be going over PWM or Pulse Width Modulation. So if you have watched the previous video, you would recognize this little setup that I have here. It was our simple LED circuit that we did in the first video, and I've just made one tiny change. I've added this button. So this button sits between the negative of the LED and ground, and it's going to allow me to turn on and off this LED. So if I press the button, the circuit is closed, the LED turns on. If I release the button, the LED turns off because the circuit is open. Pretty simple stuff, right? Okay, let's say I want to dim this LED. So right now this LED is at maximum brightness and I want it to be dimmed to 50%. So just imagine half of this brightness. So how will I do that? So right now I have the button. Let's say I just do this. Okay, I'm tapping it, and I just do it really fast. So do you see the LED becoming dimmer? No, you would think this is stupid, right? Like, this is literally just flashing. You're not fooled by the fact that I'm pressing the LED on and off very quickly and that you would see a very bright LED and then see a very dim LED or off LED, and then you see a bright LED and see an off LED and see a bright LED, and etc, etc. But you wouldn't see half the brightness of the LED. Like, you would clearly see the LEDs being turned on and off very quickly, but you could still see that. So what if I told you that, well, if we did this fast enough, if my finger was able to press this button fast enough, you wouldn't be able to notice that the LED is turning on and off, and you would instead notice that the LED is half the brightness. So you might think, wow, that's kind of nonsense, right? Well, that's the point of today's video. We'll be talking about this exact thing, which is pulse width modulation. Okay, so now that we've got that little demo out of the way, let's talk about what exactly pulse width modulation is. So, I'm gonna bring my whiteboard. Okay, pulse width modulation, as the name suggests, means that we are changing the width of pulses to create an illusion or create an effect of analog output, when in reality we're actually just using digital output, which is just 1 or 0. So a quick recap: digital is two values, which is 1 or 0, whereas analog is a range. So it's range that can be between 0 to some value, like say 255, 1023, etc, etc. These are just values, so it's just a range. So if I have a digital output, I can only output on or off. If I have an analog output, I can output a number, like some value, say a voltage value between 0 to 5 volts. Perhaps I can output the intensity of sound, the speed of a motor, stuff like that. These are all analog values because they are not just on and off. They have a range to them. So how do we achieve an analog output using digital values? So in the earlier example, we used the switch to turn on and off an LED, and this actually can create an analog, or not say analog, but it can emulate an analog output. So how do we do that? Okay, so imagine we have a graph over here that is a graph of voltage against time. So okay, voltage against time, and let's just say that we have our voltage level, our VCC is 5 volts, and this is ground, which is 0 volts. Okay, so let's just say that we turn on our output. So 5 volts is over here. We turn on our output for a period of time, and then we turn it off. So just imagine the LED turning on and then turning off. We let it stay off for a period of time, and we then turn it on for another period of time, and then turn it off, turn it on, turn it off, etc, etc. Okay, so let's just think about what this means. So in the case of the LED, we will see it turn on and off, on and off, on and off. And let's just imagine that we do it really quickly, such that this time interval, this time interval, and this time interval are really, really small, like in the order of milliseconds or even nanoseconds. So it turns really, really, really fast, and our eye isn't able to keep up. So what do we observe? We would see an average of half, or perhaps if I were to tell you that this was equal to this, we would see an average of half, because half the time it is on, half the time it is off. What is in between 5 volts and 0 volts? Well, that's half of it, 5 volts, which is 2.5 volts. So if we were to put a multimeter or some meter on the output of this, and if this T were to be really, really small, then we would actually see 2.5 volts, and I will demonstrate that to you soon. So that's the basic idea. We can actually change the output voltage by turning things on and off really quickly. So what if I wanted to create a voltage that was somewhere in between 5 volts and 0 volts, but not exactly 2.5 volts? So let's say I wanted to create a voltage that was, say, 3.3 volts from 5 volts. Well, we could use the same idea. So 3.3 volts is, let's see, what is 3.3 over 5? It is approximately, my math isn't that good nowadays. Let's see, it is about 0.66. Should have been able to get that, but I can never trust myself. Okay, so actually it's not approximately, it's equal to 0.66. And what exactly does this mean? This means that we want the on time, or the time that's spent on, to be 0.66 of the total time. So what does that mean? So if, let's say I were to turn this on for, let's say I were to turn this on and turn this off. Okay, let's say this total time that is in this cycle is equal to 1 millisecond. Then I would want this to be 0.66 millisecond and this to be 0.33 millisecond. So how would that work? Because if we were to use, like, we were to just calculate the average of this wave, we would say that we would take 0.66 times, this is, say, 5 volts. So 0.6 times 5 plus 0.33 times, well, this is 0, which is just 0. So we would get 0.66 times 5, which is, well, 3.3. So basically the idea here is that the time that is spent on, the fraction of the time spent on is going to be equal to the output that we get. So let's actually put this into practice now. How should we do this on an Arduino Uno? Okay, so give me some time. Okay, so going back to our example over here, we see that we have a bunch of pins. So over here we have some digital pins, 0, 1, 2, 3, and then we notice this strange thing. This is squiggly sign, this tilde sign over here. So pin 3 has this tilde sign, 5 has this tilde sign, 6 has this tilde sign, 9 has this tilde sign, 10, 11 has this tilde sign as well. So what this tilde sign means, it means, well, over here it does say what it means. It says PWM. So it means that these pins are capable of doing this on, off, on, off, on, off, on, off, and create this, emulate this analog output by just turning the digital output on and off really quickly. Okay, so let's actually see this in practice. I'm going to migrate over to my Arduino IDE, and then we are going to see how we actually write code to do this. Okay, so we are here in our Arduino IDE, and let's actually get cracking with some code. So the first thing we need to do is, let's just first do our standard stuff, which is to enable serial.begin, not whatever I was trying to type. And let's, what's going on? 115200 is my baud rate of choice. And let's just start with enabling the pin. So pin mode, let's choose pin 10, because that's a PWM pin. Let's call it the output, because it's going to output the value. And then we're going to go into our loop. So actually no, let's just keep it in setup for now. So we're going to tell the Arduino IDE to write an analog value to the PWM pin 10. We're going to use the AnalogWrite function. So AnalogWrite 10, and then we're going to choose a value. So how can we choose this value? Well, this value can be 02255, because this is an 8-bit DAC, digital to analog converter. So I can choose a value between 0 to 255. So I'm just going to choose 127, because 127 is approximately between 0 and 255, approximately. Okay, and then I'm going to leave it as that, and going to upload the code. Okay, so I've uploaded the code and nothing's happening. Why is that? Because, well, this is still connected to 5 volts and ground, so it's not going to do anything because we are not controlling it via the pins, which is pin 10. So what I'm going to do is I'm going to remove, or perhaps I'm going to disconnect the resistor from 5 volts. I'm going to put it on another random column, so making sure that I actually use the same column for the other pin. So I'm going to put it one on column 7, which is where our LED is located, and one on column 4, and then I'm going to connect column 4 to the pin 10. So that's going to be a bit of a challenge because it's really far away. Okay, perhaps I can make it easier for myself by moving this a bit closer to column 5. And then I'm going to find myself a really long wire. Actually, why not just use some jumper wires? So this over here is a jumper wire. It's not as good as the single core wires because its connections are a bit more iffy, but in this case we need the length. So connect it to here and connect it to 10. So 8, 9, 10. And oh dear, it's not turning on. Oh, because of the button. Okay, we forgot about the button. Let's get rid of that because we don't want to use the button anymore. And let's just put it here. So, okay, we see this LED lights up. How are we going to tell if it's actually half the brightness? Well, we got another LED. Now let's put that on. So I'm going to get myself another 100 ohm resistor. So once again, for safety reasons, or perhaps for the sake of our LED, I'm going to measure its actual resistance. We can never take the value that is in the box too seriously because we never know when we mess up. Okay, so 99, that's approximately 100. Good, we can take that. Let's connect it one end to the 5 volts and another end to here. We don't really have much space, so we're going to be a bit conservative on the space, and then we connect this back to ground. Oh no. Oh, really iffy. Oh dear, this one didn't light up anymore. Okay, so I don't know if you can tell. Maybe I should turn off the lights. I can zoom in. We can see that this LED, which is the one that we put on half brightness, is somewhat half the brightness of this. Well, it's not that easy to tell on camera, but from my perspective, it's around halfway there. So that's how we know that this PWM thing is working, because the brightness is going to be half, since half the time the LED is off, or perhaps approximately half the time the LED is off. Okay, so that's great. Now let's look at some coding examples of how we can use a certain function in code in C++ to do some interesting LED displays. Alright, so we are back at our Arduino IDE, and let's start to write some code to achieve this light effect. So before everything, let's actually write down what we actually want to achieve. So the goal of this code is to create an LED effect, or perhaps to create an LED effect where the LED goes from totally off to totally on gradually, and then from totally on to totally off gradually, and this cycle will repeat forever. So that's what we want to achieve. Okay, so now that we've learned that we can use AnalogWrite to write some value to the pin between 0 to 255, we can actually achieve this quite simply. So if we think of if we think of our goal, which is to increase the brightness of LED from 0 to 255, we could actually just say AnalogWrite 10 0, and then we could delay, because we don't want the light show to happen too quickly, because our human eyes won't be able to perceive it. And then we could say AnalogWrite 10 1, and then we could delay again, and then we could say AnalogWrite 10 2, and then so on and so forth. delay first, and then we could just copy and paste this entire chunk, and then continue by saying 3, 4, 5, and then so on and so forth until we reach AnalogWrite 10.255, and then we delay, and then we go back down again. So AnalogWrite 10.254, and then 253, 252, and then so on and so forth until we get back to 0. And then once we reach the end of this this loop, it will just loop back to the top, and the whole process will repeat again. So we could do that, but that doesn't sound very efficient, because we will be writing 255 times 2, perhaps 255 times 2, which is, I believe, 1050. No, not 1050. 450 times of this AnalogWrite, and then we have to write another 450 times of this delay, and then it just doesn't really make sense, because even if we did copy and pasting, that's really a lot of code. So how can we streamline this process? So the first thing we need to learn is that there's this thing in C++ called a while loop. So what is a while loop? It essentially is like a loop that will happen over and over again. So code in this curly braces will be executed so long as the condition in the standard braces, or in the while braces here, is true. So how does that work? So if, let's say, I put in a condition which is, say, x is equals to 1, so double equals is not an assignment operator. It means that we are checking if x is equal to 1. Then if, so long as x equals to 1, the code in this this curly braces, or in this scope, will basically just execute over and over and over again. Okay, so that's one condition. We could also say x is smaller than 1. So this is the inequality sign, which means smaller than 1, larger than 1, small equal to 1, larger than equal to 1, so and on and so forth. There's a lot of things we can do. We can use all sorts of operators, conditional operators, to check if the conditions are met. We could even we could even say if x is smaller than 1, and so this means that both conditions must be met. So if x is smaller than 1 and x is larger than 0, so that is the condition that we want to set. So x must be both smaller than 1 and larger than 0, and there's many things you can do. So the point is that while this condition is true, code in these braces will run. Okay, so well, how can we apply that to our problem? So, well, we want to increment the value of this LED's brightness. So basically the value that we pass to AnalogWrite, we want it to increment until it reaches 255, and then we want it to go back down to 0. So, well, maybe we could start by creating a variable. So So we use the unsigned 8-bit integer, because unsigned 8-bit integer has a maximum value of 255, which is perfect for our case because we only are going to 255. So let's just call this x, and we say it's 0, and then we are saying that while x is smaller than 255, we will do some things with it. So while x is smaller than 255, well, we can first say AnalogWrite 10, and then we can say the x. So we set the value of the AnalogWrite to x, because x is firstly going to be 0, and then we delay a bit. So we delay for maybe 10 milliseconds, and then we say x equals to x plus 1. So we increment x, or you could actually write it using the shorthands x plus equals 1 or x plus plus. So these are basically just the same thing, but a shorthand for writing it. Okay, so what's going to happen when x is smaller than 255? So x starts at 0 because we've just declared x to be 0, and x is smaller than 255, yes, because 0 is smaller than 255. Well, it's going to go in and it's going to say, okay, we're going to write x to pin 10, which x is 0, okay, and then so we write 0 to pin 10, and then we delay 10 milliseconds, and then we say x becomes x plus 1. So now x becomes 1 because 0 plus 1 is 1. Okay, and then we go back to the top. X is still smaller than 255 because 1 is smaller than 255. Therefore, we write AnalogWrite 10. We write 1 to pin 10, and then we delay 10 milliseconds, and then we say x is x plus 1, so x equals 2 because x is 1, and 1 plus 1 is 2. So we go back here, 2 is smaller than 255. Okay, we write 2 to pin 10, delay, now x is 3. 255, x is 3 is too small than 255, and then we just repeat this over and over again until finally x is going to be 254, and then 254 is still smaller than 255, so we're going to write 254 to pin 10, we're going to delay 10 milliseconds, and then we're going to write, we're going to change x to 254 plus 1, which is 255, and then when we come up here now, 255 is no longer smaller than 255, so this is going to be false, and this whole thing will it'll basically just stop executing because this condition is no longer true. This condition is false. So we will break out of the while loop and continue on our way. So then we will continue the rest of the code. Okay, so what this essentially does is it will essentially write the value to the analog to pin 10 using AnalogWrite, and that value will increase from 0 to 255, and then it will continue on with the rest of the code. So that's pretty much what we want for the first half, which is to gradually turn on the LED. So from 0 to 255, this code will accomplish that. And if we think about it, we can actually just do the same thing for the other half, which is say x is larger than 0. So now x is 255 because when we came out of this loop, x would be 255, and then we would want to bring x back down to 0. So as long as x is larger than 0, we will first AnalogWrite x to 10, and then we would delay, and now instead of incrementing x anymore, we will actually just decrease x. So x equals x minus 1, or x minus equals 1, or x minus minus, and then this whole process repeats until x becomes 0, and therefore 0 is not larger than 0, and we break out of this while loop. So this should give us the intended outcome. So we just use these while loops to create our LED effect, but this isn't the most efficient way of writing code, because if we see, we had to declare an x variable, and we had to write this thing down here. This is possible, but not exactly the best way to write it. So what we can use instead is this thing called a for loop. So a for loop is essentially the exact same thing that we've done here, but just condensed. The syntax is condensed. So the for loop is quite similar to the while loop. So for, and then instead of having just a condition, we actually have a bunch of things. So the first thing we have is this creation of a variable. So as you can see, this is exactly the same thing as we did over here, just that now it goes in the for loop. Okay, so we create this variable called x, we set it to be 0, and then we set our condition, so x must be smaller than 255, and lastly we set our increment operation, or perhaps the operation to execute if this condition is true. So this actually does the exact same thing as what we did in the while loop, but it looks a lot neater, and we can with one glance at this, we immediately know what's going on. Whereas if you have a while loop, these are all spread out throughout the code block. If your code gets much more complicated, it may be more difficult for someone else to be able to understand what you're doing, and it's just not as clean as using the for loop. But functionally, they are doing the exact same thing. Okay, so now we've had the for loop. Now let's just do the exact same thing. We can say AnalogWrite. We can write x to 10, and then we delay for a bit, and then we don't have to increment because the incrementer is already here. And interesting thing is that unlike our while loop where we incremented the x at the bottom, in this case we increment the x right before everything. So essentially the x plus plus is sitting somewhere here. So the x plus plus, or the x equals x plus 1 happens at the top rather than at the bottom. This is just how the for loop works, and actually we can actually show that. So I'm going to, we've already initialized our serial, so I'm going to actually just say serial.print line, print.print. I'm going to say current x value and then I'm going to print line. So basically to just create a new line after the print, I'm going to print X. So what this does is this allows us to see what exactly is going on under the hood. So if the increment happens at the top here like so, then we should see 255, because the idea is that X is going to be 254. So let's say X has gone from 0 to 254. So X 254 is still smaller than 255. Okay, so we go in, and if this were to be up here, then basically 254 would become 255 because X would increment by 1, and we should see the X value as 255. So we should see this line which says current value X value is 255. Okay, but if the increment operator was all the way down here, then we wouldn't see 255, because, well, when X is 254, this would be true. We would come in, and then we would see the X be printed out as 254 because it's not incremented yet, and then it would do this analog write delay, and then it would increment the X value, so it'll be 255, and then when it comes over here, now 255 is no longer smaller than 255, this condition is false, and this all this stuff wouldn't run. So we will not see any line which prints current value is 255, because the case where the X is 255 and this gets printed, well, it doesn't exist, because if X is 255, then this condition is not true anymore. So we will see that we will indeed see the this print say X current value is 255, proving that this X++ does happen right at the start. Okay, I flashed the code, and as you can see, the LED is growing brighter, but really, really slowly. So I'm going to change the delay to 10, and let's just see how it goes. So I'm going to change the delay to 10, and I'm going to upload the code. So we should see that the LED just, goes up and down much faster because it's going to delay less. Yeah, then we'll see that. Let's just let my compiler do its thing. It's a bit slow, and we should see that soon. Okay, so it's done. It's uploaded, and we see that this thing goes up, goes down, goes up, goes down. It has this fade effect. So that's exactly what we wanted to achieve. All right, so that pretty much almost sums up this session, but just a little interesting point. I'm going to demonstrate what this PWM looks like. So I'm going to introduce you to this new piece of equipment. So let me zoom out a bit so you can see it. It's called the Digital Storage Oscilloscope, or DSO. In this case, this is the DSO138. It's a really cheap DSO with quite good functionality. It's up to 50 volts, and it's pretty good for the price you're paying. It's really not that expensive, about 40 bucks, and it gives you tons of features. So how do we use a DSO? That's not really part of this video, but let's just say that the DSO can it graphs voltage over time. So it shows you how the waveforms of voltages, shows you how the voltage of things change over time. So I'm just going to run through how exactly this works, as in a very brief explanation of how to set the thing. You have ground, which means that this connector is connected to ground. You have AC, which means that it will show both positive and negative. You have DC, which just shows positive, and then of course this sets the resolution. So the higher you go, the less you see, or perhaps the higher you go, the less detail you see, but the more things you see. And this of course also sets the size of the box, or so basically the scale. And these buttons basically would just toggle through all the various functions. So you can change the sampling, you can change the time axis, you can change the type of trigger, stuff like that. These are all, I'll do a video on this another day, but today is just not the day. Okay, but what we came here for is to actually look at the waveform of this PWM. So I'm going to put this wire onto the oh no, it went off. Onto the pin that actually feeds the LED, that feeds the PWM, which is the pin 10 itself. So I'm just going to stick it in. Hopefully this doesn't ruin the connection. Okay, so it's still going strong. Okay, and I'm going to connect the positive lead of the DSO to this pin 10, and then connect the negative lead to ground. and something bad happened. Strange. Okay, but what? Can I try that again? Did I make a mistake somewhere? I don't really think so. Okay, never mind. I'll just leave it. I don't know what's going on. Okay, but let's turn this to DC. I don't know why that caused my computer to complain. Whatever. Okay, so over here we see the waveform. Let me just zoom in for a bit. Okay. Okay, so here we can see what PWM really looks like. That's what we discussed. So it's going from 0 to 100%. So it means that, or perhaps, yeah, so it means that at 100% we see that the whole line is at the high, which is 5 volts, around 5 volts, and at 0% we see that the whole line is at the bottom. So as it toggles through the two between 0 to 100%, we see that the time spent on gets greater, sees the time spent on getting greater, and the time spent on getting smaller. The time spent off getting greater now, see getting greater, and the time spent off getting smaller. So by changing the fraction of the time that on is being sent, we actually directly control the brightness of the LED. So let's just put LED side by side so you can see. Okay, so when it's at a maximum, when it's at the maximum brightness, see that the line is all the way at the top, and when it's at the minimum brightness or off, it's all the way at the bottom. So this change in duty cycle basically controls the brightness of the LED by turning the LED on and off so quickly that our eyes can't really see the individual switching, and it will be tricked into thinking that the LED is actually getting dimmer and brighter. So this doesn't just apply to LEDs. This can be used for motors. It can be used for various things. And this is just a simple example of how PWM can be used to change the apparent voltage across an electrical device. Okay, so I'm back at the Arduino IDE, and let's look at the serial monitor to see if what we've discussed earlier regarding when the increment happens is indeed valid. So right now it's just spewing out all the values of X. So I'm just going to turn off the auto scroll. Okay, and we're going to start to look for the 255. So okay, over here, nope, this is going down. Okay, so hold up, what's happening? Okay, all the way here, somewhere here. Okay, so wait, what? Where did it go? Okay, I think the problem is that the thing is spitting out a number, so every time I try to move the cursor, move the scroll bar, it gets the position gets messed up. So I'm just gonna unplug the Arduino from the board because it's really just messing up the formatting of everything. So I'm gonna scroll down, and alright, over here we see the current value of X is going to be 254, and then it's 255, and then back to 254. So well, that pretty much settles it. So what happened in the code is that the value of X was compared to 255 first. So well, it's 254, this was true, and then it was incremented immediately. So it would have gone from 254 to 255, and then this thing prints zero print X, which then gives 255. So if this was at the end, if the increment was happening at the end, then we would not see a 255 because this would print 254 and then increments to 255, and then when it comes back up, well, 255 is not smaller than 255, so therefore we would never see a print of 255. But well, this shows that the increment does happen at the top, so maybe this would help to clarify stuff. Alright, in any case, there you have it. So with that, this comes to the end of this video. Thank you for watching. Stay creative, keep hacking, and I'll see you next time.